Good morning again, everyone. I'm glad to get to meet a few of you a little bit more personally yesterday at the tour. So thanks to the people who came for that, and thanks again for your participation in this long workshop and just staying with us for all these days. There's a lot of information, I understand, and so we try to keep it interesting. So today we're going to be talking about data analysis for untargeted metabolomic studies, and this is a place where I'm sure many of you have questions. So do feel free to interrupt. Also, at the end, I can take questions that are maybe a little bit more complex. If you have, I've done this, and how would I go about analyzing this kind of thing? So, we'll go ahead and get started. So objectives for today's talk is just to understand how we analyze and align untargeted metabolomics data, briefly some things about our quality control measures, and then understanding our untargeted data report, those people who have received reports from us, kind of just going over what the report looks like and what you would expect from untargeted metabolomics report. Back here on the workflow diagram again, similar to what we did with the targeted analysis yesterday. I mean, all the the core does everything, including preparing the samples for analysis. I mean, everything past the quenching the metabolism, this part. Right now we're talking quite a bit about peak detection, quantification, identification, a little bit about statistical analysis because our basic report will provide some statistical analysis for you. The majority of the stats analysis and the pathway mapping and such will be talked about by Ala and George this afternoon. And I mentioned that because one of the things that happens sometimes with untargeted metabolomic study is, what we can do for a basic analysis maybe doesn't incorporate all of the factors that you have, you have, because a lot of times people will give us, a couple factors, but really there's all this clinical data that they have that maybe need to be considered. And so the statistical analysis is sort of an ongoing, often an ongoing endeavor that goes on beyond the end of the study and when we've turned over the initial data to you. So just wanted to mention that. So this is sort of a workflow that we do in our lab. It's not necessarily universal in the sense that all labs will do the same steps, but we have sort of a unique method for doing our data analysis, and I'll kind of try to explain that using the workflow diagram. So there's this right path, and then there's this left path here. So the right path really all refers to how we initially came up with our identification scheme for untargeted metabolomics. We have, I think I mentioned, a library of I really think it's about 1,000. We've kind of lost count because we've just added stuff over the years. It started out being about 850 metabolites. We have an entire compound room devoted to this. Now it's probably over 1,000 of these are authentic standards that we've purchased, and so we've created a library on our reversed phase chromatography. And the things that kind of go into creating a library is to obtain the MS data and or MSMS if you're going to create a MSMS library, and then there are some things that are unique. Like for example, when you're looking at standards, you might want to note that the primary ion, the molecular ion, is maybe not necessarily the most intense ion because things will happen where some compounds really like to pick up a sodium adduct, and I'll talk about what addicts are a little bit more later, but that is something that you want to capture in your library. You want to capture, what is most likely to be the most intense form of this particular metabolite so that you don't miss it later on when you're trying to match against it. So this part all happened sort of before we really started running samples and before we really, started, running the untargeted metabolomics workflow for people. And this is the sort of ordinary sample analysis. So the first thing is, we'll run the the samples on the instrument, and you will get raw mass spec data, which, you know, we looked at what, you know, the isotopes and all that stuff looks like yesterday. The next thing is to extract something called a molecular feature. So I just want to explain what a feature is, because you may hear about that in literature, or, you know, through us talking about metabolomics, whether it's untargeted or targeted. So a feature is really, it's something that we defer from calling a metabolite, because we don't know if it's really a metabolite. We don't really know if it's something that is interesting to you. It could be an artifact. It could be an exogenous compound. It could be something that happens in the instrument that is sort of a breakdown product of a metabolite. So we start by just calling it a feature. And there's a little bit more that goes into what a feature really is in terms of the way we do the analysis, but I'll explain that again later. But think of it, to begin with, as just, it's some signal that we've detected, at least a single peak that has some mass and some retention time. So the process is to go through every data file and find all the features. And then there's sort of an alignment step that happens where, you know, now you want to figure out if the feature in sample A is the same as the feature in sample B, and how do I align that, and how do I decide if those two are the same thing? And I'll talk about that in more detail later. We would, you know, kind of filter for consistency once we've done some alignment and some additional analysis. We would sort of go through and say, well, you know, we're just maybe going to get rid of something that's only present in 20% of all the pooled samples, for example. But again, we'll go into more detail later. Then in our particular workflow, we take these, the library of the authentic metabolites, and we sort of combine it with the data, and then we again do an alignment step where we're looking at how well does a library entry align with your data, and is that alignment sufficient to call that an identification? And I'll go into more detail about that later as well, which is this part here. There are a couple different ways to remove redundant entries. I'll talk about that in another slide soon. And then there will be performing some kind of statistical analysis and generating the report. But the big picture is that we have to somehow determine what the features are, determine if they match the library, and then sort of start to get rid of some things that are redundant, and then perform a statistical analysis. Yes?
For the extract molecular features, do you subtract blank?
We do not. We do have a library of some sort of known unknown contaminants that show up in sort of blanks on a regular basis, but we don't do it on a per sample basis or on a per analysis basis.
So different samples go through different sample prep. Do you always have a blank for those set of sample, or you have some just known masses that you think those are always in the blank?
Yeah, essentially we just have some known ones. I mean, I think you run into the difficulty of when you're looking at a blank that, you know, without a person really looking at it, you don't want to get rid of good data. So you want to be really careful that you're not, you know, applying something you're seeing in a blank to, you know, across the board. I think it's better to sort of build up a library of knowledge of what some of these known, unknown contaminants are, and approach it that way. I mean, that's how we usually handle it. And I can explain a little bit how we do that later. All right, go on. Okay, so going back to, this is maybe very basic for some of you, but I just want to make sure that everybody understands kind of what we're talking about. So yesterday we looked at, and I think, you know, Charles and I talked about what an extracted ion chromatogram was. So that's where you are looking at a particular mass that's been detected in the mass spectrometer, and you're saying within a very tight mass window, where am I seeing this peak? And if your mass accuracy is good enough, if you can tighten that window down to 1 or 2 ppm, you may only see a single place in the chromatogram where that peak comes out. This is called a total ion chromatogram, which is quite a different thing, because you can see sort of like a bunch of different peaks here and features. And again, for those people who don't know what that is, essentially what it is at any given point along the elution from the chromatographic column, it's the sum of all the ions that are coming out. And underlying this is a number of different scans. So essentially, time of flight. The ions going down the flight tube are like summed together, and then they become a scan. So you can sort of discretely walk through this, like, in our instrument, it's 0.06 seconds, I believe, for each scan. So you can discretely see what's coming out at any given time. But generally, when we do this, we're going to kind of look at multiple scans back and forth and try to see if the same ions are present in this scan and the next scan and the next scan. So you can look at a single scan, or you can average scans together to look at what's coming out at that time. So the chromatograms always kind of go from low to high in terms of mass. So you can think of it as at any given time in the chromatography, all of these ions are being observed, and they sum up to some intensity here. The reason I mention that is because this is what we're talking about when we're talking about finding features. I want to be able to make sort of a mass list of all of the things that are seen here. And there's, some very large ions, there's some very small ions, there's some noise we want to filter out, and we want to, be able to say, but what are all the things down here? Because really sometimes the low intensity stuff is important, and it's what you're really looking for. So each of these sort of particular ions here, or this, has that same isotopic distribution that we talked about. You just can't see it because it's all kind of crunched together. But so if you were to expand this out, each of these would have their own sort of isotopic distribution, which allows us to do some other things with the data. So let me go forward. Okay, so again, going back to, if I just took this little slice right here, which is kind of a broad peak, but again, this doesn't represent one compound. It represents all the compounds coming out at this time. And I took the top several ions here and did an extractile chromatogram. This is kind of what it would look like. I'm distinctly, I see that there is, some separation, possibly baseline separation between this ion, which is the 157 Dalton ion here, and this one, which is the 221. So they kind of are separated, don't really overlap. They overlap obviously a little bit, or they wouldn't show up in the same mass spectrum. And then this one's a little bit earlier. And then these two sort of look like they collude pretty strongly. So that may mean something to us later on. We might want to see why are those two things colluding so strongly, and why do they, if they have the same peak shape, does that mean that they're related ions? So we'll talk about that later. So, oops, went too far. So most labs, ourselves included, will use some kind of software to do the feature extraction. And there are a number of decision points within the feature extraction that you can make. You can say, I just want to look at molecular ions and their isotopes. So in other words, I want to treat every ion as if it were a distinct thing, but I do want to collapse the isotopes with it. So in other words, I go back 2 slides. I don't want to pick this as a feature and this and this. I know that these at least all belong together, so I'm going to collapse those into a single feature. That's one option. There are, a lot of other events that happen in mass spectrometers. You get what are called adducts. So in other words, you need some kind of a charge to be able to detect the ions. So in positive ion mode, you either get that charge through protonation, or there might be other events. If you're using any kind of glassware anywhere in your process, you're likely to get sodium and potassium. If you have ammonia in your buffers, you're likely to get ammonium ions. So, and then negative mode, they either lose a proton or gain a chlorine. But there are other choices you can make based on your chromatography, what kind of additives you put in your mold phase and things like that. There's pros and cons to letting the software pick a bunch of different adducts or ion choices. And you can imagine that a pro is that you might think that the the more signal I can gather together into one metabolite of interest, the more likely that signal is to sort of average out to be maybe a little bit more stable over all the samples of interest. So, so in other words, if some percentage of my ions are picking up a sodium, would it be good to be able to get the ones that are not sodiated and the ones that are sodiated together? Because, on average, my quantitation might be better. Okay, the flip side of that is true. If you decide that you're going to collapse the sodium ion in with the molecular ion, then if it misses it once, then that kind of might skew your quantitation. So there's pros and cons to doing it either way, and we'll talk a little bit more about that later as well. But at any rate, you have to sort of let the software do that, and if it will do that for you, you'll see fewer features that are reported out because it will take two distinct peaks that belong together and sort of collapse them into one feature. Does that make sense? Are there any questions about that? Okay. All right. So, these metabolites come out with multiple forms. And this is just an example of a spectrum where this is actually sort of the parent ion here, the metabolite of interest. And this particular metabolite really likes to pick up sodium. So it actually, the sodiated form is the most intense. And then here it also, a smaller percentage of it picks up potassium. And then down here, you can get dimers of it. So you get two of these kind of connected together with the sodium. And so, essentially, this is just an important point because what it turns out is in your untargeted metabolomics data, you have a lot of features that are related to each other that are all exactly co-eluting, and you want to try to reduce this down to, one ion that best represents all of these ions here. And the reason you want to do that is, there's a number of reasons. Statistical analysis, you want, you're going to be able to, the more of this redundancy you get rid of, the more likely you are to be able to bring your false positive discovery rate down to something that's rational, and you're not going to be able to have to do a lot of cutting off. So, so just to show you how this comes out, if I were to tell it that I wanted to look for all those things, then it would sort of collapse those features into a single metabolite, a single compound. And at the bottom here, on some of our reports, you'll see, you will still see an annotation file, which actually will tell you all of the ions that were collapsed together to form a particular feature. All right, so that's just the first part of it, which is to really kind of decide, what things you want to go into a particular feature. Do you want to collapse some of those ions together, or do you want to treat them all as sort of separate? Once you do that, there's a step which is essentially then saying, okay, I found all the features in sample A, all the features in sample B, and now I need to go back and sort of align those and do what's called a recursive analysis. So alignment is probably more related to your chromatography. If you have, really excellent reproducibility, then when you look at your peaks, they should all line up anyway. And so that step may not be particularly crucial if your chromatography is not great. Some of the software can, sort of start to bring those peaks back into alignment by adjusting retention times. But the recursive part of it is probably the more important part. So what the recursive analysis will do is it will go back and it will decide that you have a feature that's present in, say, 80% of the compounds of the samples, but is not there in the other 20%. And so it'll specifically go back and look to see if that feature is in the other 20%. So you ask yourself, well, why does it miss it in the first place? So it's a good question, right? If everything's aligned and if the retention times are the same between all the chromatograms, why does the software miss certain features? So one reason might be that the sort of mass tolerance or the retention time tolerance was just a little bit outside of what we used to find the initial set of features. So, we had been very stringent and said the first time around we want you to align features that are only within, like, say 10 ppm from each other. And I was going to put in a slide about what the mass accuracy, what ppm means, but it's the width in which you are considering two things the same mass. So if I have a very stringent criteria for that the first time around, I might widen that out, and then it will go back and say, okay, well, this one has the same retention time, but instead of being 0.001 Daltons away, it's 0.002, and I'll consider that to be the same ion on the second pass. Another reason is that, as we talked about, so when you have the option of collapsing those features into a single feature, you might find that it's possible that this feature might become part of this feature in 80% of the samples, but for some reason the software didn't think that they were exactly colluting, that exactly have the same peak shape. So therefore, in a different sample, it might call this and this two different things. And the recursive search will be able to go back and sort of say, well, if I'm not finding, if this is what it called in 80% of the samples, but it's not finding it the second time around, it can go back and say, oh, it was really there, but we collapsed it in this feature, and we didn't collapse it into that feature, in another sample. So after the recursive search is done, there's still going to be some missingness, and George talked about that, imputation strategies for dealing with, and he may talk about it more today, for dealing with missingness. No software is perfect, and we're talking about, for untargeted metabolomics, there are usually, depending on, different labs out there are doing different things, and there are a lot of decisions that go into how you do the peak picking, but could be anywhere between 4 and 6 or 8,000 features that you're finding. When you apply filtering, if you say I want to only look at features that are in 70% of the samples, or if you could say I only want to look at features that are in 70% of one group. So if you tell the software ahead of time what your groups are, then you're not penalizing yourself for saying it's only in 70% when it could be missing in 1/3 of your groups, and that's your 30% right there. It could be something that's completely missing. So there's different ways of doing it. You can either just say across the board, I just want to look at features that are in 70%. You could say, in this case, we did say in one experimental group. But I'm saying some labs may say, well, we don't have enough information based on the study design to say that we're going to filter based on number of groups. We're just going to filter across the board, and people do that. So again, if you're talking about up to 4,000 features or whatever the case may be, you're going to have some errors there. You're going to have some missing values. The software is just not perfect at always finding and always integrating the same peaks. So yes. Okay, so we have a couple different pieces of software from Agilent, and so what Steffi was asking was if there's a difference in the feature extraction between two pieces of software. One is called Qualitative Analysis, and the other one's called ProFinder. What my understanding is that the molecular feature extraction is the same. It's the same algorithm. The recursion is slightly different. They have made some changes in the ProFinder version of it that supposedly are improved. So, I'm sorry, did that answer your question? In terms of the algorithm, strictly speaking, the algorithm is the same for just the molecular feature extraction, but the recursion algorithm is slightly different. So, I mean, Sasha's here and he can speak to this. Their software, Agilent software, which does the recursion, which is called ProFinder, is, you know, up to a certain point, maybe 6 months or a year ago, was a little bit too slow to really do large batches like we needed it to do. And so the same software, more or less the same algorithm was available in sort of a batch mode thing where you could do it offline. So to answer your question, I don't think there's enough data out there yet because it's only really worked on these large batches that we've been looking at for the last 6 months to say whether there's enough of a difference between ProFinder and the original, you know, batch recursion that to say whether it's, you know, one's superior to the other at this point. But that does bring, you know, because we're talking about here Agilent software, which most of you guys are not going to use. So it just, there are differences in the software that's out there. A lot of labs will use something called, well, they'll be using a lot of different pieces of software. But I think you know, they're just what you should be critical about if you're using any software to do untargeted data analysis mining is really like how your statistics are coming out. Like, is it finding those peaks in, for example, if you do like we do it, where you run a pooled sample every 5 or 10 samples, you should be able to find the majority of those features in all of your pools. And if you're not, then that's probably not very good software. And so that's I guess that's how I would analyze how the results of each of the different pieces of software look. Are we finding all of those peaks in the pooled samples, and what's the standard deviation or the relative standard deviation of the areas for all those peaks in those different pieces of software? So it could definitely be done. So, okay. So this is something that we probably don't do as much anymore, which is we do sometimes try to assign a formula to the features. I'll kind of explain why we don't do it much anymore, but it is an option that can be done if desired. And then I'm going to talk a little bit about how we like automatically do dereplication. So manual, like in other words, are there some no-brainers, some things that you definitely want to watch out for when you're starting to look at untargeted metabolomics data? Are there things like, well, how do you know that if you have two very closely related metabolites that you've got the right one? So we'll talk about that in a future slide. And then again, we're going to go on and do some later statistical analysis. So, okay, so if we were to do the molecular formula generation, like as I showed the other day, you have an isotope distribution which is unique based on the molecular formula of a compound. So it should have a natural abundance which is representative of the atoms that are in that particular metabolite. So you can work that backwards as well. You can say if I have a very accurate mass and I see this particular isotope distribution, can I then predict a formula for this particular ion of interest? And so we do that, and some of our older reports will include that, and the software will actually sort of draw the structure on there for you if you really want it to. The reason we don't do it routinely anymore is because there are, once you start thinking about some atoms that you're going to definitely see biologically, and the uncertainty as to how many copies of any atom might be in a particular formula, then you start to get a few more errors. So when you start adding like phosphate and sulfate and things that can happen that are definitely present in biological materials, but most of your compounds probably don't have those, then your chances of picking up a formula that are incorrect are greater. So you'd want to actually sort of look at it. If you do a molecular formulation generation, you definitely want to look at it and be critical and say, does this really look like what it should look like, and does that make sense? Does that particular formula make sense based on your other knowledge about the samples? Where it's coming out in the chromatogram. If it's coming out really early and it's telling you that it's a really hydrophobic compound, it's probably not right for reverse phase. So I just want to point this out. If you get reports from us that you're going to see like sort of, again, 1 or 2 or 3 different kinds of data that comes out. You'll see named compounds, and so you'll just have your named compounds here, your samples across the top, and your areas here. And then again, if we did the molecular formula generation, if you have a little bit older data set, you'll see some of the compounds will have a formula. Ones that don't in this report, for example, without my glasses on, it's really hard to see. Line 98 here, one that just has like a mass at or retention time, that's what that means. So mass at retention time would be something it couldn't find a formula for whatever reason. If it doesn't have any isotopes, it can't find a formula, for example. But in general, we more or less report everything now as just mass at retention time or a named named compound, and that's fine, because if you're going to go on and do any kind of further analysis with this, then really kind of just having an accurate mass and a retention time are probably 2 of the most important pieces of information you need. So again, these are all those unknowns that the different people in the group have been talking about. Sub mentioned that when he did his analysis, that they really kind of focused down on the named compounds. For various reasons, they did not want to deal with the unknowns. Maybe they didn't want to, find biomarkers that they later needed to really have to dig in and figure out what they were. And I say that because what we're going to see later on is that a lot of times some of the unknowns are really related to the knowns anyway, and that you may or may not gain a lot more information from that. It's really important if you're going to include all these unknowns in some sort of biomarker discovery, that you're going to be critical and do some data reduction before you get to that point. All right, and also within our reports, you'll always see a QC report, which will tell you sort of what the RSD of all the internal standards that we've added were over the entire course of the run. So typically, these will tell you a couple different things. We have 2 different types of internal standards. One is that we add at the point of extraction. So in other words, that one will go through all of the steps with the sample. And for our untargeted metabolomics platform, we actually have do a dry down step where we'll take the extract, we'll dry it down, and then we'll bring it back up. And so this will, it will tell you a little bit about recovery. In other words, so if we're having pretty consistent RSDs over all the samples, then our recovery of that sample when we've brought it back into solution was pretty good. We also have another internal standard that we add to that resuspension buffer. So we've dried down the sample, resuspending it into the mobile phase that we're going to use for the run, and we will add a second internal standard for that, just to kind of get 2 different measures of what's going on. One is how well do these things dry down and then come back into solution. The other one is just how well the instrument itself is performing if you don't take any of the preparatory steps into account. Okay. Oops. Go ahead. All right. So so as you have seen, based on that previous slide where we showed that one compound can appear as a sodium, potassium, a dimer, and such. It turns out that in untargeted metabolomics, this can be a big problem, because as much as probably 50 or 60% of the data that's reported out by not just our lab but by other labs may be what are called redundant features. Again, these are things that are really features that represent a metabolite, another metabolite there. They all represent the same metabolite. And then, what do we have? We have maybe of what's left, about 50% of them are known, and or 40%, and another 60% are unknown. So we're going to talk about strategies for dealing with those unknowns and strategies for dealing with these redundant features. So what are those? Okay, so I also want to mention what are the different signals that you'll see in an untargeted metabolomics study. Obviously, if you've done a lot of this, you've thought about this before, but those people who haven't really done it, obviously the metabolites of interest, which are endogenous, drug metabolites or other exogenous compounds. Now, obviously, those can still be of interest to you if you're doing some sort of environmental study. Background ions, which are the ones that I said that we kind of keep a list of these known unknowns that we're going to start to try to subtract from the data just to get rid of. And then contaminants that you believe arise from sort of the sample prep at any point. Things that might come from gloves, things that, we talk to people and we do a lot of consultation, and we're kind of always careful to make sure that people are being really careful about how they're doing their metabolomics, because sometimes when you start to see samples coming in with different polymers in them, you're like, how could this have happened? Probably don't want to do metabolomics in the same lab where you're doing a lot of gels, so you're getting SDS into all of your glassware and all of your samples that those can show up as polymers in a metabolomics study. And then there are peptides which could be endogenous, but also could be just breakdown products from the from proteins. So, sorry, without my glasses on, it's really hard to see. I think this is sort of a similar thing, just saying that we have an extracted ion chromatogram, and then we have a total ion chromatogram. Obviously, even if you have, for example, an accurate mass, and you've done an extracted ion chromatogram and you've filtered down to a pretty tight mass range, you may see multiple peaks in the spectrum that represent the same mass. Now, if you're lucky and your mass accuracy is good enough, these peaks represent constitutional isomers of each other. So in other words, you can say that these actually represent a single formula, but the different connectivity of the atoms. So even if you have perfect mass accuracy, you may still see multiple peaks, because anytime you have a metabolite that has the same atoms, it's going to have the same mass. So if your chromatography is good and you can separate those out, then that's ideal. But there are situations in which things that are only slightly different from each other, an OH group is in a place, but it's pretty close by, so it doesn't really affect the retention too much. Those things may either coelute or come very close to coeluting. So I'm going to talk a little bit about how we deal with those as well. And I'm going to have to go backwards. I'm sorry. This is not the most recent version of the. Somehow when I uploaded the wrong one. So that's okay, but I'm going to skip those slides and I'll come back to them. So let's just talk. So then, like I said, we will do all those steps, the feature finding, the recursion, trying to go back and remine the data to make sure that we have aligned the peaks and made sure that there is, as representative as they can be to the best of our knowledge. And then if you give us groups, we will go ahead and do some statistics for you. A very early and useful tool might be to do a PCA plot, which you've heard a little bit about so far in this workshop. In other words, and so essentially, when I have just a few groups, two or it could be more, how well do they separate from each other? Are there definitely metabolites that I'm finding that delineate these two groups from each other? And so that's just sort of a quick way of seeing, yes, there's a signal there that's different between these two groups. We will also report a fold change analysis with p-values and corrected for multiple corrections. Again, so you're looking at knowns and unknowns here. So this is definitely something where at this point you're probably going to come back to us and say, what can we do about this? Because most of our things that are highly significant are unknowns. So how do we deal with that? And again, we'll talk about different strategies for that in a moment. Okay, so our initial, soon I'm going to talk about some software we developed, and there was a poster out in the lobby as well, to really get down to the business of reducing these redundant features. But initially, there are some things that we try to do, and I just want to make you aware of it, because if you're receiving a report from us, it's important to know. If we do have unresolved isomers, so in our library, when we ran a bunch of samples, like for example, we ran a bunch of standards, for example, all the hexoses. If we decided that they were too close in retention time to each other to really be considered, you know, separated on the chromatography, then what we would do is we would have sort of collapsed those down and just kind of report the most biochemically probable compounds. So in other words, you know, most likely you're going to see glucose, and because it's the most abundant, and not necessarily a bunch of other hexoses that are that may be sitting under that glucose peak. If we have a compound that's detected in both positive and negative ion mode, we try to figure out which one is the best representation of your for your data, because, you know, based on like RSD, like which has the best signal and you know, is the most reproducible, and we'll just report the one that's the most reproducible. And then we try to make sure that when we name the compounds as well, that we don't have redundant features. So the software will sometimes pick the same feature twice, even though they're really close together in retention time. There's just every once in a while it'll do that, and so if that gets named twice, we try to reduce that data first before you get it. So going back to the concept of, sorry, trying to go back a little bit. Okay, I don't know what I'm doing here. I'm sorry. Okay, well, let's just talk a little bit about, so you saw the slide where we talked about how maybe as many as 60% of these compounds may be considered what are redundant features. They're features that represent the same thing. I think part of the way we originally found this was through Alla Karnowski's work and George. You want to be able to take your metabolites and kind of start mapping them to pathways. And so, as you'll hear a little bit more about later, I think you can't always just map your metabolites to pathways. Either the pathways are, you know, not necessarily correct in terms of the actual biology going on, or you have compounds that don't have a KEG ID that is easily mapped to a pathway. So what Al and her group have done is they're looking instead at correlation networks. So in other words, how are all the metabolites that we are detecting, you know, related to each other in a network, as opposed to being mapped onto a pathway per se. So when you do that, you see not only, you know, named compounds, but you start to see a lot of unnamed stuff that shows up in a network. And so, you know, I really wanted to get to the bottom of like, what is all this unnamed stuff that is showing up that's, you know, that, you know, potentially could insert itself between two of our known metabolites, and you know, that doesn't tell us anything about the biology. So in this case, they didn't insert themselves in between, but it's potential that they could. So so I think Charles Evans, and this is very early days when we first started doing this, helped her, and you know, kind of went through and was able to sort of, for the most part, figure out what all of those were, and they turn out to be, you know, essentially either adducts. So, you know, we've picked up a sodium ion and we haven't collapsed it into that feature, so it's come out as a separate feature, or neutral loss events. So in mass spectrometers, things can fragment in the source before they get into the mass spectrometer. So it's kind of I say it's kind of like you're getting a pseudo MS spectrum. So your main peak of interest is sort of falling apart in the source before it even gets into the instrument. It has exactly the same chromatographic time because it was a single compound as it was coming down the HPLC column, but when it got to the source, just before being detected, it kind of started to fall apart. And so there are a lot of what are called neutral loss events. And so the way you would know that would be that would have a mass that's lower than your compound of interest, and then you could figure out what the difference was and say, does that correspond to some, some fragment that, or some loss of some group that makes sense? Is it a loss of water? Is it a loss of COOH? Is it something that makes sense with my molecule of interest? So, so we decided that we really need to get rid of that data because, we're not interested in all of these redundant features and all of these neutral loss events because they don't tell us anything about the biology. We just really want to see proline and alanine and such. So based on that, we wrote a program called Binner. And what Binner does is kind of unique. If you use XCMS or some of the other software that's out there, there are annotation programs that will go in and try to say, I can name a feature that's related to your feature based on some mass difference, but they don't necessarily take advantage of the fact that how well things are co-eluting. And in theory, they do because they look at peak shape and they look at retention time. But we think that we have a more unique way of doing that, and I'll explain how we do that. It's basically based on retention time bending, which is easier to see in the next slide than it is to explain. But it also applies chemical knowledge to eliminate redundant peaks, not fails, and I'll explain what that means. Okay, so this is kind of like a big picture of what Binner does, and this is just a small part of all the ions that we detected for a particular study. And this study had perhaps 4,000 ions that we detected or features. So what Binner does, first of all, is it sort of takes advantage of the fact that even though there's stuff kind of continuously coming out over that total ion chromatogram, there usually are some breaks where there's just no ions detected. There's times when there's large spans where there aren't any breaks, but when there are breaks, we can take advantage of it. So we'll say, okay, anytime you see a 0.05 second break, or then split that data into a different bin. So you can't really see that here because this first column here is the bin, and all of these things kind of came out continuously at the beginning of the chromatogram, but that's okay because once we've decided that things are in a certain bin, we also then start to cluster them. So before we bin them and before we cluster them, we take the correlations of all the metabolites against each other over all the samples in the study. So, figure out which two things are rising and falling together across the various samples, and calculate the Pearson correlation for those. And then once you separate them into bins, then again you can sort of decide within a bin, are there some things that cluster together and have higher correlations together than other things. And you can sort of start to see this is just a great visualization tool. I mean, if you arrange the data in clusters, you can see that each of these clusters actually has like 3 subclusters, maybe 4 in here. So we believe that this really only represents 3 features, even though there's probably 15 or so peaks there, or 13 or 14 or whatever it is. But so then the trick is really to try to figure out what's the one feature that we want to retain from that bin. Okay, thanks, Hala. And so just to be very clear that the software is in development still, and we're working on it. We're going to publish it this summer. But we start. The next thing we do is we just say, okay, let's make an assumption that the highest intensity peak in this cluster is probably the molecular ion. It's the thing that we're interested in. And let's take some mass differences between that peak and all the other peaks that are in the cluster. And then we start to say, do those mass differences do they correspond to anything that we know? Do they correspond to a sodium peak? Do they correspond to a loss of carboxylic acid? Do they correspond to some other kind of, we have a lot of addicts in our list now, but the other thing, no, I'll go forward. Let me go forward. So anyway, this is generally what it looks like. So you'll start to see, so maybe in this one, these are each distinct things, 1, 2, 3. There's one thing in this bin, 4, 5, 6. So we just taken about 15 or 20 points of data and reduce it down to about 6 things. And in some cases, this is pretty extreme. In the case of, you know, when phenylalanine comes out, because it's a really abundant feature, it can generate all of these different ions. So it can generate dimers, it can generate trimers, it can generate neutral loss peaks, it can generate, you know, other addicts, sodium and potassium formate and things like that. Surprisingly, one of the things that came out of this that was interesting is that even if we don't know what an addict is and we're working on trying to figure that out, if we see the same mass difference over many bins, over many data sets, we're like, well, that has to be some kind of an addict. We don't know what it is, but it's exactly 83.0 or 969 down to the 3rd decimal place or the 4th decimal place every time. So anybody who's using this software can sort of customize it to their own experiment, because you just start looking for repeated losses or repeated addicts that you're seeing over and over again. And so again, we took all of this data and reduced it down to one molecular ion, which is phenylalanine. And again, that you could say, well, would you rather add that all up, or would you rather just get rid of everything and keep one representative ion? I guess that sort of depends a little bit on the intensity and the RSD of that compound to begin with. If it's very good, then probably just retain that one peak in the first place. So another thing that's really interesting about the software that sort of is beginning to surface more and more as we look at some of this data is we're also beginning to see that there's a lot of chemical information here that we're going to be able to take advantage of. So as we talk about trying to identify some of these unknowns, first we have really, by reducing the data, we're getting the targets down to things that we know are probably real metabolites of interest, meaning that they're things you can do a database search on and probably find a match for. If it's something that is plus a sodium and you're not telling the database that you're interested in something that has sodium attached to it, then it's never going to find it. But if you're just really looking at sort of a neutral peak, then there's a good chance that you'll be able to make a database match to it. But we're also, seeing, in a lot of places that, there are related ions that we can start to look at as well. So if I do identify this one and then I figure out that this one is, really just has an additional oxygen in it, someplace it's a hydroxy version of this or something like that, then that's more chemical information I can use to really try to identify both of these together. Likewise, actually, when we identify some of these neutral losses and we identify, especially the neutral losses, those are things that give us information about the compound of interest. So, if we've lost COOH, then there's probably a carboxylic acid group somewhere in this molecule. If I've lost NH3, then there's probably an ammonia somewhere in the molecule. So we actually retain this information in terms of when we want to do an identification and say, is the identification we made consistent with what we've observed for all these different events that we've seen? Another thing, I showed you earlier a slide where the sodium ion was the most intense. And if you do this frequently enough, you start to sort of say, well, the sodium ion is going to be most intense if it's one of a particular number of classes of compounds. And probably certain lipids are really always going to have a more intense sodium peak than the non-sodium. So you start to say, well, if I see a compound where the sodium addict is more intense, it might be a lipid. It might be a fatty acid to be exact. So we're using all this information to to help identify these compounds. So part of my talk I skipped, and I've only got like 2 minutes left, was we're going to use all that information. We're going to use the fact that we have a very good idea that this is a molecular ion, that this is not some oddball fragment, and be very aware of that. And then if we still can't identify it based on something in our library, or starting to look at what the fragments are, well, obviously you can do MS analysis, where we're going to fragment these peaks and try to do a mass match against a library match against an MS spectrum. So so that would be, and I'll be very close. Okay, now my very, very brief about that, to say that we use a number of techniques. Metlin would be one where you essentially fragment your ion of interest, you collect a spectrum that has your parent and all the fragments, and you tell it some things about the about what you expect, whether it's a molecular ion or whether it has sodium or things like that. And then you'll try to do a database match, and that's based on usually similarity to a spectrum that's been stored in that database. So somebody has taken a spectrum of this authentic compound, uploaded it to this database, and then how similar is my spectrum to the spectrum that's in the database. And somebody asked a question yesterday, like, why aren't the peaks always the same? Well, lipidomics is maybe a slightly different different situation, because their databases are mainly in silico, so they're just theoretically generated. But for metabolomics, there are a lot of reasons why this could not match. And the first reason would be just that the type of instrument you're using really affects what kind of fragmentation you see. The more energetic your fragmentation, or your then you might see more peaks here in your spectrum than they would have seen when they did it. Another thing that sort of over the years people have figured out was that people were uploading spectra of authentic compounds, which sort of were contaminated with other compounds. So you may, the spectrum that is in the database might have more peaks than you have, because some of them maybe don't actually belong to that compound. So that's something to always be careful of. And likewise, if I'm not careful and I'm fragmenting two things at once, my spectrum might be a mixture of fragments from two different compounds. So, but I have to wrap it up. But I just want to say, so, the BINNER program and the work we're doing on that is really, to me, going to increase the universe of known compounds that we're able to provide to people. And we're happy to kind of continue working on untargeted data with people. After you get that initial report, we go back and sort of identify some of those unknowns through the use of this data reduction and then further techniques we talked about. So, all right, thank you for your time. Any questions right now, first of all? Yes. Can you use the microphone or speak loudly, one of the two?
So maybe I missed the point. So let's say I have one control and one may actually sample, and we run everything on that LC mass spec and pass through algorithm and pass all the criteria. Then it generates a table in Excel form. Now I want to see where the difference between two sets are and what mass can you do with that algorithm. I just want to see the difference between two sets.
Well, the data report you'll get will have ANOVA or t-test or whatever is the appropriate statistical tests that have been run on it, and you will get some, p-values and fold change analysis. So and I think others are going to talk about the statistics more, so I didn't really cover that. But so you'll already have some sense of what what the differences are between your groups. And also, like, for example, like a PCA plot will tell you if we're able to see any separation. There are always situations in which there's too many factors that have to be considered, and you're not getting good separation just based on what you thought you were. You thought that the main effect that you're looking for was going to be diet when in fact it was age. And so unless you control for age and or adjust your data for age, you won't see any separation just based on diet alone, for example. So those things, if you don't see a result in the PCA plot, then you have to start digging further and further down to say, okay, what could it be that's sort of masking my signal between, you know, what I think that I should be able to see a difference in, for example. Does that answer your question? You would get, for the untargeted metabolomics, you would get a basic statistical report with either ANOVA or t-test and then a PCA plot. Does that answer it?
I think so.
Okay, all right, thanks. Any other questions right now? Okay. All right, and then we'll go with who's next. George.
So we'll continue with statistical analysis.